So we explained in the last section the shortcomings of the route that gives you the kinetic enolate and then the one that gives you the thermodynamic. Even though you can produce a large percentage of the kinetic enolate, you'll still get a low yield when you use that enolate in another to produce something else, if you use it as a nucleophile. So we need alternative ways. So there are alternative ways to alkylate the ketones. And let's look at the first one. So the first one is called the alkylation of an acetoacetic ester. So an acetoacetic ester is this one right here. So you have an ester right here, have an acetyl group. Now the pK of this is around 11. We need to write that down. This is important. When the reaction takes place, you have an H here. You have two of them, but we're going to remove only one of them. We're going to produce T. So you have, of course, HOET. So once again, this deprotonated one of the H's. So if you would like to see it, we'll put the and that's the negative right there. Now, once again, we know the pK of alcohols is around 15 and ethanol is around 17. So the shift will be toward the weaker acid, will be toward the weaker acid. So that's where the equilibrium will shift toward the product because this is the weaker acid. So that's how we're able to generate more of this enolate. Once again, this enolate is generated because, again, you have stabilized by resonance. It can again accomplish resonance on both sides right here. Now, the enolate of an active methylene compound are nucleophilic and react with alkyl halides and tosylates in a typical SN2 reaction to introduce alkyl group to the alpha position. So by the way, this is really this. Here's an H. It's nice to write it this way because we can just show the arrows very easily. So what's going to happen is that this is going to be your nucleophile. And this is your electrophile. So this is a leaving group. Remember that. And what's going to happen is we will have the and of course we attached this CH3 right here. And of course, the process can be repeated by adding additional base. So you know that this is now going to so if you add more base, And by the way, you don't have to draw it this way. You can draw it, you can keep it like that. That's absolutely fine. Once again, it's sometimes drawn like this so that we show the movement of the arrow very, it would be very clear, but more clear. So it would have, so you would calculate again. And then now you actually added both groups, as you can see right there. So this is why this reaction is very beneficial. So again, this is an SN2 reaction. We have a leaving group. We have substitution taking place. The best way is to have methyl primary. So this is a methyl. You can have a primary allylic, primary benzylic substrates, as we discussed, like these. Primary methyl, etc. So all of those, yeah, doesn't work well for secondary and tertiary substances. So do not use. Not very helpful. So I'm talking about if you had this and then you had something like a BR here, you can see that this is crowded. So this is sterically hindered. And this is only a secondary, let alone that if you have a tertiary, it would be even worse. So a tertiary would be like this. So this one is even more sterically hindered. Now we need to talk about an important reaction that you will see actually in biochem, especially like when the formation of histamine for allergic reactions, it undergoes a mechanism called decarboxylation. It's actually a very simple mechanism. It's very quick and it's concerted, and we need to actually learn about it because we're going to see it also in this chapter. So a decarboxylation of what we call beta dicarbonyls. So the loss of carbon dioxide is basically from here. This becomes carbon dioxide. So we're going to show you more in depth in a real example. But basically what forms is RH. So this R group has a hydrogen attached to it. And then of course, CO2 becomes a gas. And the arrow, if you ever see it up in chemistry or in biochem, it means it's bubbling away. So there are certain carboxylic acids that readily decarboxylate. So decarboxylation means the removal of carbon dioxide or the loss of carbon dioxide. So this is called beta keto acid. You have a carboxylic acid, then you have a ketone attached to the beta. So to the beta carbon. So this is the alpha, this is the beta. The product of this would give you a ketone. So it's a useful reaction because we can actually form a ketone. Very well. So this is acetoacetic acid, as we said before. And the mechanism is the following. And we need to actually, let me redraw this because we need to show that exactly. Okay, so we're going to do a switch here. We're going to rotate this, switch these two. So the OH, so you can rotate this that way. And you have the OH, and then you have the carbonyl oxygen. Okay, so what's going to happen is that I'm going to draw a dotted line there. And then we're going to use different color. So this is concerted. What's going to happen is that these electrons are going to shift down, form a double bond. This bond is going to break, form a double bond there. And then these are going to go and form a bond between the oxygen and the hydrogen. So track the movement. And if you track the movement, you're going to form an enol. So this is a CH2. You have two H's here. Plus, of course, what came out? CO2. So here's a C, double bond, O from here. I like sometimes to highlight this so you can see it. Which is that right there. Now, what did we form here? We formed an enol, and we know that enols easily tautomerize to ketones. So you can then so it would become basically this one right there. I'll draw it here.